We wanted to use our chemistry skills and knowledge for a real-world application. Biodiesel provided an interesting challenge for an experimental design and calculation. It also represents a possible alternative to fossil fuels. Finding an alternative to fossil fuels is one of the most important challenges facing our generation, and the sooner we start working on that solution, the better. We decided on using 3 different types of vegetable oils to determine which produced the most efficient fuel.
To begin the project, we needed to do some background research on how exactly biodiesel was created. The basic idea behind biodiesel is to transfer organic hydrocarbon bonds, which can release large amounts of energy when combusted, into a structure and density conducive to use as a fuel. This involves removing excess materials found in organic mixtures and creating long-chain, energy-dense hydrocarbon structures.
The process we decide to use is known as transesterification. This involves reacting alcohol with an acid to create an ester. Plant oils are composed of triglycerides, which are esters with free fatty acids containing many hydrocarbon bonds. The density of hydrocarbon bonds on the fatty acids make them ideal to be used in a fuel.
Once we had an understanding of the process, we were able to develop a procedure. The basic plan was to mix methanol with the catalyst, sodium hydroxide, and then mix the product, methoxide, with the oils. This would yield biodiesel and glycerin.
The following is a list of materials we needed for our experiments.
The sodium hydroxide came in bead form, so the first step before it could be added to the methanol was to crush it into a fine powder so that it could more easily react with the methanol. After crushing, it was massed to 0.875 grams.
Once the sodium hydroxide had been crushed and massed, it was added to the methanol and mixed until it had completely dissolved. The product of this reaction was methoxide.
With the methoxide prepared, 250 milliliters of each oil were measured with a 1 liter glass graduated cylinder. The exact amounts of oil were measured and recorded.
It was necessary to clean the 1 liter graduated cylinder thoroughly with soap and water to avoid cross-contamination. In order to completely dry the graduated cylinder, acetone was added to the graduated cylinder and then blown dry.
Once measured, the vegetable oil was poured into already mixing methoxide. The reaction is visible almost immediately.
The oils need approximately 20 to 30 minutes before the reaction is completed.
Once mixing had concluded, qualitative analysis of the oils were taken. All 3 oils had a similar white band of some kind sitting just below the surface. This was documented, and the oils were stored in a fume hood. A wait period is required before further analysis can be conducted so that the 2 products, glycerin and biodiesel itself, can separate.
In order to test how the fuels compared in efficiency to each other, we needed to separate the biodiesel from the byproducts and burn the fuel. By assuming all of the heat energy produced by the burning of the fuel would go directly into heating an amount of water, we could effectively determine the change of temperature of the water based on the fuel burnt. This assumption is supported through Hess's law and would allow for a determination of joules per gram of energy of each of the fuels.
10 days later, the change in the appearance of the oils was very noticeable. The glycerin had settled at the bottom, a film had gathered at the surface, and a white material had appeared in some form throughout the oils. We will be discussing these byproducts further later.
The apparatus as pictured right was constructed in order for easy measurements and heat conservation by creating a closed system. To ensure that the system could be assumed to be as close as possible, a tinfoil shield was constructed and placed around the setup. Other considerations made were that the thermometer needed to be positioned so that it would not be touching the sides or bottom of the can, and instead just the water inside. Also, the flame from the crucible would need to be just slightly below and in the same position for each trial.
To ensure that what we were burning was pure and as true to the other samples as possible, a filtration was performed. This was important as some of the fuels were more cloudy than others, and the filtration worked to remove these materials. While pouring into the funnel, it was important to avoid transferring the film that had formed or the glycerin that rested at the bottom.
Lamps were labeled and each filled with one of the three fuels. These lamps were masked and then placed under the apparatus. 3 empty soda cans were also labeled and had approximately 75 milliliters of cold water added to each. Cans were masked and also added to the apparatus.
Before we could begin the burn, it was necessary to calculate the in temperature. With RT standing for room temperature and WT standing for water temperature, this formula ensured that the total amount of joules needed to change the temperature was consistent throughout each trial and accounted for the differences in water temperature and changes in room temperature. The in temperature needed to be calculated independently for each trial.
One problem we ran into was the wick not catching fire. To remedy this, the wick needed to first be doused in the fuel. To do this, we simply flipped the container so that the wick would absorb enough fuel to begin burning. Once doused, the lamp burned as planned.
The wick was lit and the shield was closed quickly. The thermometer was closely monitored so the flame could be extinguished as soon as the in temperature was reached. To account for any amount of extra heat, a final recording was taken after the flame was extinguished. After the lamp was cooled, it was masked.
Some additional steps were taken to identify some of the more unexpected results, such as determining what exactly the white material was. To determine what the material was, a sample was extracted and placed into a test tube. We hypothesized with our reactants that some soap would be created, so we shook the materials mixed with water to see if bubbles would form, indicating soap. They did, and to also confirm this, we did a pH test which came up basic, further confirming it. This makes sense because the Na ions from the sodium hydroxide took no part in the reaction to form the fuel and likely bonded with excess hydrocarbons.
As predicted, glycerin formed at the bottom of the container. The amount seemed to be relatively consistent and would be interesting to see if by adjusting the amounts of reactants, if the glycerin formed could be lowered, as it presented a challenge in separation.
With all of our qualitative and quantitative data collected, it was now time to set about determining which of the fuels was most efficient and possible explanations for the results. In addition, comparisons to other forms of fuel could be drawn and an analysis of potential errors in calculating values.
In order to compare fuels, the amount of energy per gram of each fuel was calculated. To do this, we found how much energy was used to change the temperature of the mass of water and found how much fuel was burnt in order to reach this change. The formula for this was delta E equals Sm delta T, where S equals the specific heat of the water, M the mass of the water in the can, and T the change of temperature of the water in the can. This found the change of energy of the water, and by finding the change in the amount of fuel in the lamp before and after, we could determine how much energy the amount of fuel released, or the energy density. This was repeated for each of the oils.
Through our calculations, we found that the most effective fuel was created by olive oil, yielding 18,000 joules per gram. Canola was the second best behind olive, providing 4,000 less joules per gram, with corn last, providing 9,500 less joules per gram. The energy density calculations should be very close, but possibly a little off from their actual values due to some of the energy escaping and not going directly into the heating of the water. This energy escape should be fairly minimal, however, and the ratios of effectiveness are accurate because all fuels were burnt in identical conditions, meaning any energy that did escape would be uniform throughout the different trials. In short, these numbers may not be exact for the joules per gram of each of the fuels, but olive should be better than canola and canola better than the corn. These results were slightly surprising, for corn often comes up as a common source of biodiesel. We set out to find any possible explanations for results that could confirm our findings. We started looking at the molecular makeups of each of the oils, specifically the percentages of saturated, monounsaturated, and polyunsaturated fatty acids. The saturation of a fatty acid refers to how many double bonds it contains. A saturated fat contains no double bonds, and an unsaturated fat contains one or more double bonds. Monounsaturates, as the name suggests, contains one double bond, and polyunsaturates contain two or three. The more double bonds, the more potential energy to be released, but higher amounts of polyunsaturates can lead to instability and eventual breakdown in heat and water. Therefore, there is a balance to be achieved between a high enough amount of unsaturates so that the high amounts of energy can be released, but not too many so that the fuel is too unstable to be kept until it is to be burned.
With this knowledge, our results began to make a lot of sense. Since we left the fuel sitting for 10 days before burning, some of the higher energy density contained in polyunsaturates would have been lost to decay, meaning the more stable but still energy-rich monounsaturates would be more effective. This makes sense in relation to our data, where the highly monounsaturated composed olive oil had the greatest energy density. This also makes sense for canola being our second, as it has the second highest amount of monounsaturates, and corn being last with the lowest amount. This means what we can tell from our data reliably is that olive oil has the best shelf life, energy density retention after 10 days between the oils we synthesized. It would serve to reason that corn and canola would likely perform better if burnt sooner after synthesis, but in a realistic scenario, fuel could be expected to sit around before burning. It is also important to note that values for saturation differ based on specific strands of plants and extraction methods, so it is possible that different oils could have yield slightly different results.
Our best fuel, olive oil, provided 18,000 joules per gram. To put that into context, a lithium battery provides 720 joules per gram, and regular gasoline provides 47,200 joules per gram. It is definitely worth noting, however, that all fuels have a shelf life, and the numbers for gasoline and the battery are based on being freshly produced. There is no way to determine exactly how much our fuel's energy density decayed, but from our research, we can tell it has a significant drop-off after 10 days, which is how long ours sat before testing. It's also worth noting that this shelf life is shorter than gasoline, so that's a potential drawback to biodiesel.
Another possible discrepancy is the lack of exact measurement in the amount of time the fuels mix during the synthesis. While all of them had the minimum 20 minutes, olive mixed for the shortest amount of time, around 25 minutes, while canola mixed around 28 minutes, and corn roughly 30 minutes.
Due to time constraints, some discrepancies in the amount of NaOH and oil added to each mixture occurred. While we don't think these changes would affect the energy density due to the filtering we did, and instead just the amount of byproduct, we performed some calculations to attempt to verify that the energy density ratios weren't correlated with the different amounts of oil and NaOH. We compared the differences in NaOH and the oil to the ratios of the energy density, and the results were inconclusive.
In addition to what fuel was most efficient, we learned a lot about the challenges associated with using biodiesel on a massive global scale. Some of these included the filtering out of byproducts, the relatively short shelf life, and the massive amount of agricultural land needed.
Through this experiment, we obviously learned a massive amount about the science behind and the production of biodiesel, as demonstrated through our experiment. The experience also taught us so much about the process of conceptualizing and creating experiments.
It helped us learn a lot about working independently and setting a goal and going after it. The process of designing, executing, troubleshooting, processing, and concluding upon our experiment really drew upon all that we had learned about science.
That's all, folks. Alright, we're good, dude. We're done. We're done. Alright.
You want to make bloopers?
No.
Am I going first?
Never mind, I'm just going. To begin this
We
project...
should do like a hand sign so we can find it easier. It'd be like this, restart. So when we're going through the slides and cutting it,
I feel it.
This process...
If you mess up, you can just keep going, like... It doesn't even
Yeah, okay.
To begin this project, we need to do... I don't know, if you're still doing like that when I started? Okay.
I think so.
To begin this project, we need to do some background research on how exactly... Were you doing this that time?
I looked at you.
Yeah, no, you were like this when I started talking. Alright. To begin this... Alright. To begin this... To begin this project... You're smiling. Don't smile.
That's good. This is good.
Yeah, you can... Alright.
You made this happen.
Right, okay.
Action. The sodium...
Wait.
That part worked.
Let's just do one more, okay?
Okay.
That's what they do in movies. You're killing it. It's easy.
Action. After... That's That's
Wait,
silly.
was that like that before? Wow. We're gonna get some like music coming in during the No, it's okay. Yeah, obviously you weren't serious. I don't know why I said it.
No.
Per gram of energy of each of the fuels. I'm good. I'm done. I'm done with that. Let's move on.
One take.
Okay.
Oxide came in bead form. So the first step before it could be added
No,
to
the methoxide didn't come in B form. The sodium hydroxide came in B form.
like that word up there. I put it
You
down there.
disgust me.
Action.
This is a take though. Our best fuel, olive oil, provided 18,000 joules per gram. To put that into I didn't stop at all. I'm ready to kill this first thing. I just started. Why would I do this take if I just started?
Okay, the complexion.
Our best fuel. Okay, I think I did a better job of that before, and I think we did a good job on those two. So
Hey.
pause it. We're gonna do imitation now.
Glycerin and biodiesel itself can separate.
All right,
What
I
about
messed up a
soap?
few times.
What about
You
soap?
killed it, dude. Well, no, the soap was inside. The glycerin though had to separate. That was like the band of white.
Oh, okay, the two product, but yeah, it's not,
But,
not
yeah.
the only two, but I see.
Like, you don't even know what's going on anyway.
Sure enough.
We're just science words. All right,
Action.
through. Whatever.
Oh, practice.
Yeah. No, do it.
Turn off.
Good night.